All right, thank you guys for joining us today. Welcome back to another episode of Scientifically Simple. Today we're going to be talking about engineering execution in the chemical industry. And so for those of you who are probably not aware of what this means, this kind of falls into that category of topics that we consider critical for new and young engineers who are still kind of getting out in industry and learning what it takes to be successful in this field. And so I'm going to hand it over to Mo and eventually jump back in. We'll talk about it.
Thanks, Brandon. So, as you have mentioned before we start, good morning, good afternoon, or good evening, depending on the time you might be starting watching today's presentation. So, just to be adding to what Brandon mentioned earlier, today will be the first work where we will be discussing about the hardcore engineering execution steps and milestones in chemical industry in particular, and in any other major industry in general. We will be focusing more on the chemical industry as it uniquely includes chemical engineering discipline as part of the overall project execution. So our goal is to clarify for the undergrad student as well as full-time professionals in academia how that world looks like in terms of project execution, how we get to integrate everything we have learned in school from thermodynamics, mathematics, transport phenomena, chemical kinetics, etc. in that larger picture of delivering an end valuable product from a given raw material. So the agenda of today's discussion will be utilizing a top-down approach where we can start with the overall view. Then we start zooming in, getting more and more granular, where we will eventually meet what we have learned in engineering school. Chemical industry has a lot of codes and shortcuts, so get prepared to be memorizing those type of words, like starting for now with the word EPC and what the term stands for. Then we will move on to how a project timeline would look like, from initial phase all the way to startup and handover phase. That will be followed by, we'll move from the time part into the stakeholders in that project execution umbrella. How individuals from different degrees, background, and even between different engineering disciplines interact with one another, and what are the sequences of that workflow. Then finally, into the most granular part for chemical engineers, we will get touched down what's the role of chemical engineering discipline in that workflow, what are the process engineering deliverables, and what is the natural order of those deliverables. And so what is EPC? EPC stands for Engineering, Procurement, and Construction, and it's a type of contract. EPC contracts are a form of contract used to undertake constructions works by a given private or a public sector on a large scale on a complex infrastructure projects. So what's that contract stand for? What's that contract for? Why I need that contract in the first place? Under an EPC contract, a contractor must be delivering a complete facility to a customer or a developer who needs only a turnkey to start operating the facility. Hence, EPC contracts are sometimes called turnkey construction contracts.
Yeah, so I want to spend a few minutes to talk about this slide a little bit more.
Sure.
Sorry, buddy.
Sure.
So I want to talk about this slide a little bit more before we get into the meat of it, because I know for me, I've never really dealt with an EPC firm itself, but I've dealt with firms that handled smaller segments of a project, like a scrubber design, a heat exchanger design, a recuperator. And I know from myself and my experience and your experience as well that there are certain things that I wouldn't have anticipated. Basically, just going to put this out there. Does your firm actually know what they're doing or why they're doing it, right? So when I buy a heat exchanger, it's pretty well understood what I'm trying to do. I'm either trying to heat or cool a fluid. There's a certain demand that I'm required to meet, and there are certain requirements such as material construction, real estate, things like that. It's pretty straightforward. But
absolutely,
what about a unique technology? Obviously we talked about propane dehydrogenation. That's probably to the extreme where you're designing an entire facility, and within that entire facility there are individual units that are specifically designed for that application. to me, a big miss that I've made,
Absolutely.
right? And something that I think other engineers should be aware of is challenging those firms that are handling these projects to ensure that they actually know what they're doing. I mean, Mo, you've had experience with that, right? Where you have a firm handling the bulk of the engineering and there are little mistakes being made that, you know, kind of, I don't want to say calls it into question, but makes you a little bit uncomfortable with what they're providing.
Yeah. Absolutely. I mean, like, for all the, like, you know, mentioned earlier, we are eventually going to end up as engineering grads. Either we're going to end up on the aisle of being part of a customer, where we, you know, dealing with a production facility and we are part of the team, or we are going to be, you know, on that other aisle where we are part of an engineering firm. That engineering firm can be a whole EPC contractor, or it can be just an engineering firm, or even be a subset of an engineering firm and be just a licensor. So what you're adding there is a pretty outstanding question, and that's where it comes, the fact when you are sitting with each one of those licensors.
Right.
And the biggest question that comes up, if each one of them are going to be like showing you their reference plans. That's why like a reference plan is very essential for those guys. Because at the end of the day, if someone is coming to you with a theoretical technology that on paper, or even just did not make it beyond lab or a pilot phase, you are going to be in doubt. And that's why like it's going to be hard to be, you know, it's going to be having the buffer for entrance to that market. But like if someone like, for example, in a propane dehydrogenation plant, like UOP, or you are ammonia technology provider, and those are like Halder Topsoe, for example. These guys are going to come to you and basically tell you, hey, I have this X amount of plants in Europe, I have this number of Y plants in Middle East and North America. And this is where you get the chance to be actually looking at those plants. You can actually like reach out to those customers and get all your questions answered, because there's going to be a third party that can confirm that. And not to mention their, how I can say that, they are going to be well known in the market. You will know that a given specific company from other customers, based on all these standard references, that you are going to know like if they are actually like meeting what they are claiming in terms of sales or not.
And so I'll give an example for me, right?
Yeah.
So the reason I wanted to kind of pause and talk about this further, I actually have a project that I've been working on for about a year now with a firm that's reputable, with the technology that is all over the world, that we know works. And we had an incident. And so we go back and we start looking over the design and start asking some very basic questions that could not get answered. Now, I want to restate that. We were asking some very basic questions that could not be answered by the firm that developed the technology that we know works throughout the world. That became very concerning, because I now have that technology in my plant, and I can't get these questions answered. And I'm expected to run it.
Yeah, absolutely. So that is the customer's side problem. So not yours, but like the problem is the customer normally have their engineering team, and of course like the firm that's gonna build that facility for you, they have their own engineering team.
Right.
And normally in an ideal phase, you are supposed to be having a checks and balances.
Right.
The engineering team on the customer side are supposed to be ahead of the game in terms of like asking 100%. These questions in the beginning. And that's what we are actually going to be entailing when we are talking about like the typical workflow for process engineers.
Yep.
And this is where like the process engineering first step comes into place. Yep. So normally in the beginning, these questions has to be made clear. You are supposed to be 100%. Sharing all these type of process documents. Yep. Beside the references, everything that you need. The problem is if I'm a newcomer, if I just got hired into an existing facility, and these documents doesn't exist, there is nothing legally forcing or obligating that EPC firm or licensor to provide document after they already handed over.
Completely agreed.
They might be doing it for for being friendly and for reputation and stuff like that, if it matters.
Yep.
But like, if it's something you don't need to, they are not legally under any obligation to actually provide that information. And that's like when it comes to the engineering team that actually starts this work ahead when when it was still in the early initiation kind of phase. The problem is like by the time you are in operation phase, it the probability of being able to be getting the answer is going to be damped down. And the other problem too, there is high chance if you look at all the there is also the probability, like looking at the licensors, you might actually they might try to help you, but they might not have that generation that provided that information, so they actually might not have it.
Right. And forgive me, because I really don't want to beat that dead horse, but the reason for bringing this up is the worst question is the one that you don't ask, right? So just kind of keep that in mind as we go through this.
Oh yeah, absolutely. I'm actually appreciating that you're asking those questions, because this is the type of dialogue that pretty much I'm expecting. So, but like before we move to that part, like there is so in addition to be delivering a complete facility, the contractor must be delivering. So that's what, adding to what you're mentioning, or at least partially to what you were talking about earlier, the contractor must be delivering that facility for a guaranteed price by a fixed date, and it must perform to a specified level.
Got it.
You see, it's a three-dimensional thing. That's why it's called the EPC contract turnkey. You need to be delivering the design basis. I need to be making X production that the customer wants to make, and I want it to be done by this price, because me as an investor, I'm gonna be already understanding what amount of capital investment I'm putting there. I already in the background already estimating how much that is going to give me the return on investment, etc. And I need this by fixed date.
100%.
I don't want to be ending up for example, in 10 years or so. I don't want to be I want this plan to be done in 2.5 years, and you end up with 5 years. So you need to be fixing the space-time issue problem. And failure to comply with any of those requirements will usually result in a contractor incurring monetary liability. And it's a very fair game, because at the end of the day, that EPC contractor will get what they are asking for. But if you are not delivering, you are supposed to be penalized.
100%.
So this is a very fair game in that sense. The natural sequence in that engineering project timeline. And there is a reason why you have EPC. Engineering starts first, then follows by procurement, then follows by construction. You cannot do it any other way. You cannot, procure equipment before you engineer it, for example, or you cannot construct a plant without having the engineering or the procurement. So the engineering function, there is 4 main functions in a project timeline. There is the engineering functions, there is the procurement functions, construction functions, and commissioning functions. So what the engineering function entails, it's going to be dependent on what phase you are going to start from. So if you are going to be starting from a phase where you're already 100% sure what you want to do, then it's going to be basic engineering, followed by detailed engineering, then the planning, and then construction engineering. Not the construction, just construction engineering itself. Now, if you are going to start from something like, a new technology, let's say you have a PDH or butane dehydrogenation, or you have a green technology, like where you have a solar farm that supplies electricity to make hydrogen by electrolysis, then that's not an established process yet, so you're going to have to do a feasibility study, because this is pretty much something that's new. We have no clue about the economics of that process, how much it's going to cost us, how much revenue it's going to be giving us. So whenever you have all these economics parameters not clear, that means you're going to have to start from the feasibility study. And that's pretty much what the feasibility study means. You need to basically have a crystal clear understanding of the economic value.
It's basically pass-fail for a project.
That's pretty much, Yes, pretty much. It's an on-off.
Yep.
I need to understand if it's worth
Yep.
it or not. That's pretty much what it's trying to do. If it's worth it, then you're gonna go for something called pre-feed, and it's a weird phase where it's not as detailed process as a feed phase, and it's not as primitive as a feasibility study phase. Once you go to the feed, or also as you call it, the basic engineering phase, that's where like all these process documents we're going to talk about later on in the slides are prepared.
Right.
And pretty much all the data sheets for all different equipment has been supplied by process data, temperatures, flows, pressures, etc. Now the other engineering disciplines like the mechanical engineering, electrical engineering, civil engineering, all these guys will be able to complete it and be able to send all these data sheets for every single equipment to the procurement to get out there and basically start picking who are the vendors that can provide those equipment, and of course your selection then are going to be constrained by the cost.
Real quick, so basically by the time you get through the feed portion of the engineering design, your scope should be defined, right? You should know pretty well what you're going to do and how you're going to do it. You may not know the very specific details about it, but the design is done basically. And that's really important because that's where a lot of different projects and firms go wrong, right? You'll get past feed, you'll go into procurement, construction, and then you're like, oh wait, I need to change scope. Well, you're installing it. You know.
Absolutely.
I mean, does anybody know how much it costs to change scope when you're installing a piece of equipment? It's exuberant. You know.
That's a lot of money.
And that's where a lot of projects go wrong,
spot on.
Right?
If you would look at the timeline there, from cost perspective, the earlier on you pick something, the lower the cost. As you progress, that cost grows exponentially, not linearly, grows exponentially because everything has to be restarted from the beginning because
100%
you're spread across a big web. The other side, it's reversed in terms of the process engineering, the workload. The early on, the more process work is being done. As you progress through that whole timeline, you're gonna find out that it's going to be decaying
100%.
The process work pretty much versus the other engineering disciplines, and of course it start to be peaking for the other. So pretty much the feasibility study all the way to the basic engineering / feed. That's where the workload of the process engineering or the chemical engineering is. As you progress downstream of that, the chemical engineer or the process engineer becomes a supervisory kind of work task because they are going to be reached out by mechanical engineers or other disciplines to confirm given information, just pretty much acting as a consultant at that point. Then once the detailed engineering is completed, now you already have everything mechanical, civil, electrical has been done. Now it's on the procurement department and the fabrication to start getting all these items and start to be like estimating how much is going to cost us to procure this amount of money. So that's pretty much like the procurement and fabrication. Now, once the procurement and fabrication, and why is it called procurement and fabrication? Procurement is pretty much if you have a standalone equipment that a vendor will provide. Like if I'm going to be providing an air separation unit, that's a black box. It's going to come from a vendor as a package. So that's called a procurement for that piece of equipment or a pump or something.
Right.
But if you're talking about fabrication, now you're going to be like talking about something that you're going to make from scratch. Like if you're going to basically start making pipes and you roll them and all these things, that's what fabrication means. If I'm going to be, for example, have a primary reformer, which is a fired heater, normally that's not going to come as a piece like a black box, you put it there. It's going to have to be constructed on site. There is no way around it. It's a gigantic furnace, and that's pretty much what fabrication means. You're going to have to get all these...
Another big miss that both of us have seen in engineering, right? So let's say that I'm going to take a really simple example. I've got a heat exchanger. I need 100 square foot of surface area, 4 passes. I defined the tube size and all of that. Those are very specific details that I selected for a reason. One of the big mistakes we see in engineering is procurement will say, well, hey, I can get this thing cheaper in carbon steel, or maybe a bigger tube size, or maybe fewer passes. And they'll change the design and order it based on that, and then it doesn't work.
Oh, coming from procurement, you mean?
Procurement, yes.
Well,
because it's cheaper.
that's the critical part.
Right.
So the critical part here, that's what the datasheet specification that has been already done in the basic engineering part, which is basically supplied the process data, then followed by the fact that you have a mechanical engineer that basically adding that piece of puzzle on his end. Because like when you are doing the heat exchanger, there is the thermal design that the chemical engineer would do, for example, and then you have the mechanical design that the mechanical engineer would finish. And once those are being there, the procurement only have the freedom to pick the type of material that only been specified in those data sheets. Like if I'm having telling you hey, it's only stainless steel 304, for example, that you can only use, you cannot as a procurement say a carbon steel is
but you know what I'm talking about. We've both seen it.
What's the point of? Yeah, absolutely. I mean, that's not the job of the procurement.
Right.
I mean, if the procurement can be doing that, then at this point we don't need engineers.
Right.
Because again, the objective function would be the cost itself.
Yeah.
But to be adding, at the end of the day, the objective function is to be meeting what this plant need to be making.
100%.
Production-wise, quality-wise,
100%.
time, fixed date-wise. There is a constraint on the cost. It's never gonna be the cost is do whatever, but that is called a constraint. And there is the point of having it as a constraint is that you have a very limited flexibility in terms of what you are picking for making something cheaper. So if you're talking about someone, a vendor versus vendor A, vendor B, and there is one that's local and there is one that's in Europe, for example, and you be saying both are supplying the same heat exchanger, but one is 30% or 20% cheaper. Yeah, of course you're gonna be doing that. You're not gonna buy the more expensive one because both of them are meeting. The problem now it becomes about logistics and transport costs. So yes, they have the freedom to do that, but that's part of the procurement function. So procurement functions, logistics and transport when it comes to the cost aspect for logistics and transport, fine. Invoicing or purchasing, that all these pieces that has non-technical dimension to it, they are flexible to do whatever they want with it. But when it comes to the critical data sheet that has been filled, they can't wiggle around it. And that's the whole point of having a data sheet. It's most importantly, it's very clear what you need. Because whenever you are filling these pressures, temperatures, and fluid, and how much, for example, partial pressure of hydrogen there, it becomes very clear to the vendor how he is going to spec that given compressor, for example. But if it's not clear, there's going to be a miscommunication between the engineering firm and the vendor that's going to be supplying that. Because keep in mind, those are going to be different things. A company like UOP is not going to manufacture a compressor. They're going to go, for example, to a Mitsubishi. And because you have now a contractor and subcontractor, they're going to make sure they are communicating pretty much crystal clear of what they need on both ends. So just wanted to clarify that. So with that being said, we can now be moving to the next part, which is basically now who are the stakeholders, not the shareholders. The shareholders we already know, those are the folks basically paying for the whole thing, the main investors. So this is a typical structure. As you can see, you have in any project execution, but specifically when it comes to a chemical plant execution. If you're starting from a greenfield, and when I'm talking greenfield means that there is no chemical plant in the first place.
Right.
That's pretty much like you have you're buying a land and you're starting literally from scratch to build everything.
Yep.
You might hear the other term, which is a brownfield project or a revamp project, where there is an existing plant and you are adding some equipment or even a whole process unit to that plant.
So I'll say this, Mo has actually done both. I've only had to deal with brownfield projects.
Yeah, those are the most common ones.
Right.
It's given, like the greenfield tend to be like a very intensive in terms of capital investment because you're building a whole big plant. And in terms of the risk, like when you are building a subunit in a brownfield, I mean, you are guaranteeing everything pretty much like utilities, and you have neighbors where you can actually like supply you with a given raw materials. But when you're starting from greenfield, that risk grows exponentially in terms of like what can go wrong. So in engineer, like the stakeholders in execution from engineering perspective, of course you're gonna have the project manager, and the project manager pretty much have the engineering manager basically reporting to him, and the other non-technical or non-engineering disciplines. That's the procurement, construction management, the folks that work on project controls, and administrations. So pretty much engineering and non-engineering. So what is the role of a project manager? So number one is plan and develop the project idea. So every project starts with a given idea. It's the project manager's responsibility to be working with internal stakeholders and external clients to define that concept and create a process to bring it to fruition.
Yep.
Number two, you're gonna have to create and lead your your dream team, because like now you have this privilege to do so in your position. And the project manager are accountable for every aspect of the project, including leading a team capable of meeting or exceeding, preferably, the client expectations for their vision. And of course, you're going to be doing monitoring the project progress and be setting the deadlines. Number three is you're going to have to be like solving issues that be arising in any project. Nothing is going to be going 100% as expected. There's going to be some minor random problems that might show up or challenges. So during every project, issues be arising that needs to be solved. The project manager is the first person that the clients and the team members are going to be turning to when something goes wrong. So it's in these professionals' best interest to be anticipating any potential hiccups before they happen.
Yep.
Now, the next task is going to be managing the money. This is the dude that basically going to be managing the money. This is the top of the whole organizational chart that has to be funneling how that cost going to look like, and that's their job. It's not like about like how tight they have to be around certain things that might be appearing to you critical or not, but ideally they have a higher overall view on that topic. And the budget management is another primary project manager duty. These professionals make sure that the project gets done without excessive spending. A good project manager has mastered the art of cost efficiency. So pretty much like they will always have to make sure they are building buffer, just in case something might be arising. The last two important critical parts is, of course, like ensure the stakeholder satisfactions, which basically the project manager have the closest relationship with clients of anyone who works on a project. Because of this, it's important they keep open lines of communications for updates and feedback. If there is any type of issues that's happening within the team or internally or between the team and external parties like vendors, etc., that's the guy that's going to have to reach out to. And evaluate the project performance. That's the last but not least. After a project is finished, the project manager is responsible for evaluating its efficiency and effectiveness. With the data they have tracked throughout the process, they can begin to identify shortcoming plans or ways to fix similar issues in the future. And that's what they call lesson learned. You're always going to be hearing about the term in engineering firms, what were the lesson learned? These can be like documents provided by engineers, can be documents provided by project managers or engineering managers. Everybody is basically learning whatever in their own subset of kind of challenges. So these are the roles of a project manager. Now, what's the difference between the role of project manager and engineering manager? The engineering manager is like right there, like in a very delicate, you have to be having this delicate balance between a project manager. He doesn't have the same kind of like duties and roles and responsibilities, but yet he is responsible for the project manager in making sure that everything is like working perfectly within the engineering discipline, between different engineering disciplines. And the role of engineering manager is relatively simpler because at the end of the day you're dealing with like engineers in general.
Right.
So there is no external parties, there is no vendors or something like that in that sense. Like you're not dealing with some external parties. That's the role of the project managers.
Agreed.
So the noise or the uncontrollable factors are less inside the engineering manager if you compare it with the project manager. So ideally the engineering manager should be having adaptability, leadership, organization, planning, and problem solving. So when it comes to adaptability, they have to be successful and be flexible to be changing timelines and objectives. The project manager at some point gonna be like, hey, change of plans, we need to be doing this now. Whether it's an objective change, a scope change, or timeline change. Because like this is the power that the project manager has and the engineering manager does not have. The one of the critical differences. In terms of leadership, they will be leading a team, involves motivating each member to do their best work in a collaborative process to be completing the project. Organization, and this comes when you have the document organization and meetings and everything, even when using a linear methodology, which most of the engineering manager uses in engineering terms. An engineering project manager requires organization from that manager, and an engineering manager must break the project down into its granular phases, assign tasks to different team members, and keep the whole engineering project moving
100%.
forward. That's hold the role there in terms of organization. So in terms of communication, they have to have the ability to clearly communicate what can confidentially communicated, present their concept and designs to decision makers in presentations, meetings, and reports, as well as to various teams they coordinate. Influencing outcomes. They require the skills in influencing others in order to approve or support new proposals, initiatives, and changes. Now, the last and the most important, I just skipped that for the last piece because it's the critical one. Business visibility. They have to have the dimension. They need to understand how their projects create business value so that they can preserve this value as they manage these projects.
Yep.
Because if you lose that scope, everything is going to be derailing. This is your objective function. This is your main objective function. So you and the engineering manager and the project manager has to be having this clear visibility. And that's why they need to be focusing mostly on managing the team and understanding the business value. Nobody's asking them for the technical part because their role in the beginning was to be picking the team to be taking care of the technical part.
And so, again, I want to jump in here because this is another one where like both of us having more, this is typically not done well. You know what I mean? And I'm not trying to throw anyone under the bus. I'm just trying to point out that it's not done well, and I don't really know why that is, right? So just running down the list, I can't tell you how many times I've not had the process data sheet for a heat exchanger. Literally, we were like, hey, we just need 100 square foot, 4 tubes, this size, 2 diameter, and that's literally what we roll with. No idea what we're trying to accomplish. No heat demand, no duty, just nothing. Just hey, just any heat exchanger will do. How many times have you seen the heat material balance? Because I've never seen one.
Oh my goodness, yeah.
Process and utility flow diagrams, didn't even know they existed. Utility consumption, we don't even talk about it until we don't have enough. Emission list.
So the problem was these sequences is twofold. There are two main contributors to that. Number one, what we mentioned earlier, greenfields are rare.
Yes.
So
100%.
greenfield is the luxury. They are not the common. Normally, you have a brownfield. I am changing this heat exchanger because it went rusty, or it has too much pressure drop that it keeps shutting down the plant, and it's really worth it now to change it because it has a business value. Every time we keep clogging that heat exchanger, the plant has to go down, and that's wasting this amount of downtime kind of.
Right.
That's the number one. Number two is, even if you have a greenfield, what is the probability that you're going to be having an engineer that will be seeing all that workflow? Either they are going to be joining during the detailed engineering, or maybe they have joined in the beginning and then they moved to another role, or they didn't foresee the whole sequence.
I completely agree.
So you have two layers on top of each other. What is the probability of greenfield? Then followed by what is the probability of having an engineers, or number of engineers that has foreseen everything from start to end of that plan, of that engineering task. So most of the time, even when you have an engineering project engineering that has started as a greenfield, normally you are going to find teams and sub-teams even in process, where like some process engineers are working on the like, let's for example say the reactor side of the process, and some other engineers are completely focused on heat exchangers. Some other engineers are focused on utilities. So don't think that the process engineer that's going to be part of the team is going to be like, hey, I'm going to be working on the whole ammonia plant, and I'm going to be like working on understanding all these things. It's going to be requiring a lot of dedication. It's going to be requiring a lot of purpose in actual to be reaching that point. But even when you're given that opportunity, you're going to you'll be like spending around, like if you're really up to it, 4 to 6 years to get grip on all of these things. But the sequence is pretty logical and straightforward. If you have a greenfield, that's where the process engineering starts, like we were talking about earlier, feasibility. You're going to have something called kickoff meeting. You're going to be sitting in a kickoff meeting with the customer. You are going to be the process engineer along with sales, for example, and you're going to need to understand what the plant concept is going to be about. And plant concept, what we're talking about here, it's not about the fact that, hey, I'm going to build an ammonia plant, because there are so many details beyond that. Because the ammonia plant is going to be like, am I going to just build an ammonia plant and the utilities is going to be supplied by someone else? What type of utility do I have? Do I have like water that's coming from the ocean, or water coming from a river, or water coming from a lake? What type of seismic activity do I have in this area? So you have, of course, the civil engineering going to be there. And there are so many questions that's going to be like going on between the customer and you as an EPC contractor or even an engineering firm to understand all these details. You're going to need to understand what type of raw material you're going to be using, what type of impurities is going to be there. Like if I'm going to be using natural gas, there are things that's going to be mattering in this case. How much sulfur is in there? Is there mercury? For example, because you're going to have like reactors that has catalysts and it's going to be impacting your process. If you go to another part, it's like, am I going to need to produce the steam for you, or you are going to be importing steam? When it comes to cooling, which every plant is going to have some cooling fluid one way or another. Some of them going to be like relying 100% on air coolers, maybe because that site, it looks like it's well, economically speaking, it's way better to be having air cooling system than cooling water system in terms of costs. Or if you are dealing with water, for cooling perspective, am I going to be, what source I'm going to be using? So that's going to be dictating if I'm going to have desalination or reverse osmosis, or I'm going to just jump into fluctuation because I have already a river water. That's one of the things. Also, like if you are going to be producing steam, it's going to be impacting your demineralization unit as well, because there's so many details that's going to go in that direction. But once you have completely clarified that, you need to go for the design basis, and that's where the design basis, basically the Bible of the project, is.
Right.
It's a document that basically specify in a quantitative manner everything that's coming out of the meeting that the EPC firm and the customer has agreed upon. Here is the natural gas. Here is the catalyst that we are going to be using. Here is the type of utilities we're going to be using. Here, like utilities that you're talking about, everything. Instrument air, plant air, nitrogen, cooling water, demon water, what type of raw material I have. All these things is going to be detailed there. And even the standards of codes that have to be followed. Because like, you know, if I'm in Europe, I might be having a standard of codes that might be different than in the United States. But at the end of the day, there might be standard of codes, and then on top of this, there is extra privilege on top of that. So the customer might be actually way more strict in a given equipment than the standard and code itself. So, and then once that design basis is completely agreed upon, that's where the process engineers start to be doing their fun work that we have learned in school. Start generating the heat and mass balance. Now, all the fun that we have learned in school, we're going to be doing this. The whole flow sheet that you're going to be building there. And the process flow diagram is pretty much the sketch out of that plus the numbers. And we are talking about, like, you know, material composition, what type of process those streams are going in. And we're going to be explaining this later in later episodes for sure. But this is going to be your basic foundation. And as you are moving through each one of these steps, it's critical that they are being done correctly. Because if you come later to change something, all that is going to be costing too much money. It depends, of course, where you are. If you are talking about, like, for example, in the Middle East or Asia, out of the EPC, the engineering is the most expensive part. So it really matters to be working on that getting done correctly. If you are in North America, because of the construction cost that's is pretty intensive, you are going to find out that the construction is the most intensive part of the whole process. So pretty much like you're going to find in North America, almost 60% of the overall cost of the project can be concentrated in the construction phase. Meanwhile, you can find more than 50% of the project in the Middle East or Asia is concentrated in the engineering phase, because relatively construction in those countries are relatively cheaper. So anyway, then from the heat and energy balance that you have, you start producing all these lists that's going to be essential for other engineering disciplines. You start making the emission list that's going to go to the HSAE department. That's going to need to make sure that everything that's coming out of the plant is basically following the regulations, whether it's state and federal, these laws. You're going to have to be reporting all these things. Now, all this process data that you have specified, pressure, temperatures, partial pressure of hydrogen, mass flow rates, molar flow rates, is going to go to the mechanical department. Now, I need to be doing this heat exchanger. You already provided the thermal design of the heat exchanger. Well, now the mechanical engineer has to work on the mechanical design. The same if you're going for a package unit or rotating equipment. I'm gonna need to be compressing the stream from this value to this value because it's going to be doing this in this reactor. Mechanical engineer does not care about that, but he cares that you need to specify what head I'm gonna need and what type of fluid that goes in there with the compositions, pressure, and temperatures. And of course, you go to the P&IDs, piping and instrumentation diagrams. That's where all the details keeps moving into the mechanical department, where you have to be specifying what type of piping, what type of diameters, what type of pipe spec sheet that we can have, the material of construction. All these things comes from the process. So you can see how much impactful if an error happens in the process will be have to be
100%.
redoing in that perspective. You don't need to start all the way from plan concept every single project, but this is pretty much exhaustive list that includes everything for chemical engineering discipline. So that would be it for me.
All right, so we just want to say thank you again for watching. We really do hope you walked away with something unique and different, and maybe it helped your perspective, or it helped you kind of think of some questions you want to ask. As Mo did say, if you want to reach out, ask any questions, send an email to sciencemadesimple@outlook.com. That email address is shown on the slide in front of you. Please do reach out. Muhammad and I both are active in industry. You know, we're always kind of looking for different topics and perspectives to tackle and kind of delve into. So if there's anything that jumps out that you'd be interested in, please reach out and let us know. As well, you can find us on YouTube at Scientifically Simple, and that's all I got. Signing off.